In this video, we are going to revisit the idea of cross product and kind of offer just a second geometric interpretation of that operation, and then also work a few examples of applying that. So just to kind of introduce this, I'm going to show you another formula that kind of works with the cross product, and this is the length of the cross product. So what does this length here actually mean? Because remember that the cross product actually gives you a vector back. So in order to get its magnitude, we have to take the length of that resulting vector. But this does actually have its own geometric interpretation. And what that is, we can write this using this alternate formula here. It's actually equal to the length of each vector times the sine of the angle between them, which, it looks actually kind of similar to that other definition of the dot product that we talked about a few videos back. And this angle between the two of them is exactly the same as it was then. We have the same diagram, two vectors, and then there's that angle. But this right here does not represent the same thing as what it did with the dot product, because obviously sine theta is different than cosine theta. And in this particular instance, what it's actually going to do is give us yet another way to get area of the parallelogram created by these two vectors. So this will give you the area of the parallelogram formed by U and V. So if you have U like so, and V looks something like that, then it gives you this parallelogram right here, and the area that is contained inside of this. Now, a couple of videos ago, we talked about how the determinant can give you area of the parallelogram, but determinant can only give you area of a parallelogram if you're working with two-dimensional vectors. The nice thing about this cross product is that it gives you the area of the parallelogram when you're working with three or higher dimensional vectors. So just a quick note here, this is useful for using three-dimensional vectors. Because if we take the determinant of three-dimensional vectors, when you've got three of those three-dimensional vectors, you wind up with the volume of a parallelepiped. But if you just have two three-dimensional vectors, you get that parallelogram by taking the cross product. So let's work an example of that. Okay, so in order to find this area of the parallelogram, according to what I just kind of went through, what we've got to do is find the cross product of those two vectors and then take its length. And then the length of that cross product is what's going to give you that whole area. So we start by finding the cross product. And we put the I, J, K in the first row, and then the entries of U in the second row. Just like so. And then we take this determinant here. We get I hat times the determinant of what's left over when you ignore i's row and column. So -1 times -1 minus 0, minus j hat times the determinant of what's left over. So 2 times -1 minus, oops, that should be a -3 right there. 6 times -3. And then plus k hat times that determinant of 2, -1, -3, 0. So you get 2 times 0 minus -1 times -3. Okay, so we simplify each of these components down, and you're going to wind up with this just as 1. So just I hat minus 16 j hat is what you get out of this piece right here, and then minus 3 k hat. Okay, so this is going to be our vector right here for the cross product. And then to actually get the area of that parallelogram that is formed by u and v, we have to take its length. So here we take the square root of each of its components squared and then add it up. So 1 squared plus negative 16 squared plus negative 3 squared. This is all equal to the square root of 266. And I personally have a preference for leaving things in square roots as they are. So I'm just going to leave it as such. And the area of our parallelogram is just equal to that. And so that's pretty much all there is to that process. Let's work another example. This time I'm going to find the area of a triangle that has sides that are determined by u and v. Let's say u is equal to 2, negative 1, 6, and v is equal to negative 3, 0, negative 1. Okay, so as far as area is concerned, all we've talked about is parallelograms, but it's actually really, really easy to get the area of the triangle from this. Let's just look at a picture though to see where that's coming from. So if this is our vector u and this is our vector v, we know that these form a parallelogram like so. And we know that the area of this whole parallelogram is equal to u cross v, right? That's the whole parallelogram is this guy right here. But we want to know about the triangle that is formed by u and v. And that's going to look something kind of like just this segment right here. We'll notice that this line, that third leg of that triangle, cuts the whole parallelogram perfectly in half, which means that the area that we want here is just 1/2 of the parallelogram. So I'm going to multiply this guy that gives the area of the whole parallelogram by 1/2. And this is going to be our expression for the area. Now, we actually already found the area of this whole parallelogram in our last example. And we said that that was equal to the square root of 266. That's this piece right here. And then all we have to do to get the area of just that triangle is multiply it by 1/2. So then the area of just this triangle is 1/2 times the square root of 266. And that's pretty much all there is to it. But let's work a slightly more complicated example, and we'll show it beginning to end where we maybe don't already have the area of this whole thing computed. So in this case, we're going to find, actually, let's do this on a separate piece of paper. I suspect I will run out of space. Okay, we're going to find the area of the triangle with vertices that are given by A equal to 1, 2, 3, B equal to 1, 0, 3, and C equal to 2, 2, 1. Okay, so unlike previous problems that we've been looking at, we weren't given vectors in this. We're just given a collection of points, right? And we know that we have, maybe our triangle looks something kind of like this. So A is right here, B is there, and C is this point over here. So we know that generally speaking, our goal is going to be to obtain 1/2 of the length of the cross product of some two vectors. But we don't have two vectors, okay, in this situation right here. We're just given a collection of 3 points. However, we are able to actually create the vectors that we need in order to be able to solve this problem. And in particular, we need to be able to create two vectors that share an initial point. And we can just, I don't know, we can pick any two that we want. I'm going to use AB and AC, I think, in this case. So we can take U to be equal to AB and V to be equal to AC. Okay, so all we have to do really is just create these two vectors right here, and then we're able to plug them into our formula and take the cross product and all of that, and we will get our area for the triangle. So AB is determined by taking the difference in the components of B and A. So we get 1 minus 1, 0 minus 2, and 3 minus 3. So AB is just equal to 0, negative 2, 0. And then similarly for AC, we take 2 minus 1, 2 minus 2, 1 minus 3, and that is just equal to negative 1, 0, negative 2. Okay, so now we have our two vectors, and all we got to do at this point is just plug them into our cross product, take the determinant, and then take half of that to get the area of our triangle. And here we go. So we have AB cross AC. That's equal to, oops, that should be an I hat, J hat, K hat, and then we stack AB and AC into here like so. And then we start taking our determinant. So I hat times negative 2 times negative 2 minus, and then that other diagonal is going to be 0, 0, and then minus J hat times 0 times negative 2 minus, looks like it's going to be 0 times negative 1, and then plus K hat times 0 minus negative 1 times negative 2. Okay. Simplify each one of these down in each of the components, and you are going to get the vector 4I hat plus 0J hat plus, oops, that should be a minus 2K hat. All right, so that is our vector AB cross AC, and that's kind of what goes into this right here. So now we just need to take the length of that, and that is equal to the square root of 4 squared plus 0 squared plus negative 2 squared. If we add all that up and simplify it down, it's actually going to wind up being 2 times the square root of 5, because this is just the square root of 20. Sometimes it makes it a little tidier to be able to factor some pieces out of that square root right there. And so to kind of finish this problem up, then all we have to do is take 1/2 of this guy here, which just gives us square root of 5 in this scenario. So that's pretty much all there is to this. Again, big idea here was just noting that we had this original formula. We needed two vectors that shared the same initial point to plug into it. We created those two vectors based off of the difference between the points that we're working with, take the determinant, take the length of the resulting vector, and then divide it by 2 to get the area of the triangle instead of the whole parallelogram. And that is pretty much all there is to finding the area of triangles when you're given vertices or vectors and you're working in like a 3-dimensional case. Now, I do want to take a moment to kind of clarify when you should use a determinant versus when you should use a cross product to be able to find area and volume. Now, I'm just going to make like a little table here. When you're working in the 2-dimensional case, you're actually going to get the same thing out of the determinant versus the length of the cross product. So, And actually in this situation, you really don't even want to use the length of the cross product. You just simply want to use the determinant. And this, because the two-dimensional case will always give you a parallelogram. And we're not going to use the cross product in that situation. But in the three-dimensional case, we do actually wind up with two different things depending on what you use. So in this particular instance, you're going to have three vectors, and it will give you volume, and it is a parallelepiped. In the case with a cross product, though, you're only going to be given two vectors, and this only gives you area then, because two vectors means that you have two dimensions for your space, and then that's only going to wind up giving you a parallelogram. So hopefully that helps in helping you make a decision between whether or not you should be using a determinant or a cross product. Again, just to reiterate, when you have two-dimensional vectors, so, or your vectors just have two components, you're always going to use the determinant. When you have three-dimensional vectors and you're given three vectors in this case and you're going for volume, you use determinant. And if you have two vectors that have three components, it's going to give you area and you want to use cross product. So that's all for this time. See you again in a bit.